Dear students, in this class we are going to learn the lesson number 1, real numbers. Real numbers are actually the numbers which can be represented on a number line, and the numbers which cannot be represented on number line are imaginary numbers. Real numbers include 3 types of numbers: integers, rational numbers, and irrational numbers. These are the 3 types of numbers which can be represented on number line. Therefore, these numbers are real numbers. And the numbers which cannot be represented on number line are called imaginary numbers. Numbers like minus, √1, √-3. These are the numbers which cannot be represented on number line. Therefore, these numbers are imaginary numbers. Let's come to the new topic, the fundamental theorem of arithmetic. The statement is, every composite number can be expressed as product of its prime factors. For example, we have 1771. It is a composite number because it has more than 2 factors. The 2 factors are 1 and the number itself. Apart from these 2 factors, it has 3 more factors. That's why it is composite number. And the factorization of this composite number is unique. Means there can be only 3 factors: 7, 11, and 23. There can be only 3 prime factors. This factorization is unique. We cannot take any other factor apart from these 3 factors. Therefore, the factorization is unique. We have another number, 8232. The factors are 2, 2, 2, 3, 7, 7, 7. So we can take 2 raised to 3 into 3 and 7 raised to 3. This factorization is also unique. Irrespective of the order. Order means we can take 7 raised to 3 first and 2 raised to 3 later. There is no specific order. But the factorization should be unique. That means we cannot factorize these prime factors any further. These are the prime factors. We can take only 3 types of factors: 2, 3, 7. That's why the factorization is unique. This is the fundamental theorem of arithmetic. Let's come to the example of fundamental theorem of arithmetic. The example is, we have given a number 4 raised to n. This is a series of number. Why it is a series of number? Because when we put values of n equals to 1, 2, 3, we get different numbers. 4 raised to 1 is equal to 4, 4 raised to 2 is equal to 16, like that. We get a series of number. And we have to check whether in this series of number, is there any number which can end with 0? We have to check this. To check this, we are going to use the fundamental theorem of arithmetic. First of all, take the number 4 raised to n and factorize it. We have taken 4 raised to n and factorized as, 4 is factorized as 2 into 2 raised to n. 2 into 2 means it is power 2, 2 raised to 2, bracket raised to n. And by using the rules of exponents, we can write it is equal to 2 raised to 2n. Now it is clear that in this series of number, we have got only one factor. We have got only one factor, which is 2. But if any number were to end with 0, the factorization of that number must contain the combination of 5 multiplied by 2. But in this case, we have got only 2. We have got only 2. Therefore, there is no number in the series which ends with 0. Now let's come to the concept of LCM and HCF. LCM is the short form of least common multiple, and HCF is the short form of highest common factor. What is LCM? It is the product of highest power of each prime factors. Highest power of each prime factors. And what is HCF? It is multiplication of, it is the product of lowest power of each common prime factors. What does it mean? Let's take an example to clarify the concept of LCM and HCF. Let's take 2 numbers, 6 and 20. And we have to find out the LCM and HCF of these 2 numbers. So we are going to factorize these numbers first. So factors of 6 is, it is equal to 2 into 3. Means 2 raised to 1 into 3 raised to 1. And factors of 20 are 2 into 2 into 5. That means 2 raised to 2. 2 raised to 2 into 5. And now LCM, as the definition of LCM contains highest power of each prime factor. Highest power in these 2 factorization, which is the highest power of each factor. We have got highest power of 2 is equal to 2 raised to 2. So we have taken highest power 2. Next, highest power of 3. Highest power of 3 is 3 itself. And what is the highest power of 5? It is highest power of 5 itself. We have taken each prime factor. We have taken all the prime factors. But in the case of HCF, we are going to take only common factors. Know this word. Only common factors, and also the lowest power of that common factor. In both the factorization, which is the lowest power of 2? Lowest power of 2 is 2 raised to 1. Can we take 3? We cannot take 3 because it is not common in both. Can we take 5? We cannot take 5 as well because it is not common in both the factorization. Therefore, the HCF of the given numbers is 2 and LCF of the given numbers is 2 is to 2 into 3 into 1. That means it is equals to LCM equals to 60. LCM is 60 and HCF is 2. Let's take an example of LCM and HCF. The example is find the HCF of 96 and 404. These are the two numbers given and we have to find out the HCF of these two numbers. And first finding HCF, later by using the property of HCF and LCM, we have to find out LCM. This is the question given. First of all, we are going to find out HCF. To find out HCF, what we need? We need factors of the numbers. We have a 96 given and the factors of 96 are 2 raised to 5 multiplied by 3. And the factors of 404 are 2 raised to 2 multiplied by 101. These are the factors of the given two numbers. Now, as per the definition of HCF, we have to take lowest power of common prime factors. So, what is the lowest power of common prime factor? We have common prime factor only 2. 2 is the common prime factor. But we have to take lowest power of that common prime factor. We are going to take lowest power 2 raised to 2. 2 raised to 2 means 4. Now, let's use the property of LCM and HCF. We know the property of LCM and HCF. What is the property? LCM multiplied by HCF. It is equal to product of two numbers. Okay. And from this property, if we shift HCF to the right side, it will get divided to the product of two numbers. So LCM is equal to product of two numbers divided by HCF. Now we got product of two numbers 96 multiplied by 404. And we have HCF found 4. By solving this ratio, we'll get LCM which is equal to 9696. This is how we can find out LCM by using the property. Now let's start with a new topic, revisiting irrational number. As we all know, irrational numbers are those numbers which cannot be converted into P upon Q form, where P and Q are integers and Q must not be equal to 0. Example of irrational numbers, root 2, root 3, pi. These are the examples of irrational numbers. If any number P divides the square of another number Q, then in that case, the P divides Q as well. Now example, if 2 divides 2 square, it means that 2 should divide 2 as well. This is the fact, we know this. And next, this fact is applicable only for rational numbers. This fact is applicable only for rational numbers, not for irrational numbers. If any number found not following this fact, then that number is irrational. And we are going to use this fact to prove irrational number as irrational. We have discussed the facts of rational and irrational numbers. In terms of irrational numbers, the irrational numbers cannot be converted into P upon Q form. It is a fact. And the second thing is, for rational numbers, we have discussed if the number is converted in P upon Q form, then it is called a rational number. We are going to use this fact to prove irrational number as irrational number. Root 2 is irrational. We have to prove this. And we are going to prove this irrational number in 2 steps. The first step is assumption. The first step is assumption and the second step is contradiction. First step is assumption. We have to assume that root 2 is not irrational, but it is rational. If root 2 is rational, then we must be able to convert root 2 in P upon Q form, where P and Q are integers and Q is not equal to 0. Also, assume that P and Q are coprime. This is our assumption. This is very important assumption. We have assumed P and Q are coprime. What is coprime? Coprime numbers are those numbers which do not have common factors other than 1. Now, this is our assumption. And in the next step, we are going to square the equation. We are going to square the equation. Squaring both sides of the equation, we got root 2 square is equal to P square upon Q square. Next, it will become 2 is equal to P square upon Q square. Okay, if we shift Q square to the left side and 2 to the right side, we'll get Q square is equal to P square upon 2. It means that this 2 is dividing P square. If 2 is dividing P square, that means 2 is dividing P. And if P is being divided by 2, that means we'll get P is equal to 2C. 2C, some other integer. Why? Because after dividing P, we are getting some other integer and we have considered C as that integer. So P is equal to 2C. Okay, where C is an integer. Now put this value. Put this value in equation 2. When we put this value in that equation, we'll get Q square is equal to 4C square upon 2. After solving this, we'll get 2C square. And now, when we shift 2 to the left side, it will give us Q square upon 2 is equal to C square. It means that this Q square is getting divided by 2. And if Q square is getting divided by 2, it means Q is also getting divided by 2. It means that P and Q P and Q, both the integers are getting divided by 2. But this is a contradiction. Why? Because we have assumed that P and Q are co-prime. But now we have found that P and Q are getting divided by 2 other than 1. So P and Q are not 2 prime. This contradiction has arisen just because we have assumed incorrect. What we have assumed? We have assumed that root 2 is rational. And this assumption went wrong and we got to know that root 2 is irrational. It is proved. Let's take another example to prove that 5 minus root 3 is irrational. Okay, we can prove this by assuming that 5 minus root 3 is rational. This is our assumption, step 1. And if it is a rational number, 5 minus root 3 is a rational number, means we can convert 5 minus root 3 in P upon Q form, where P and Q are integers. Now rearrange the terms in equation 1. Rearrange the terms in equation 1, we get 5 minus P upon Q is equal to root 3. Now it is equation 2. It is clear that from this equation, integer, 5 is integer, P is integer, Q is integer. Means integer minus rational becomes rational, the left side becomes rational, and right side is irrational. Means both sides are not equal. If both sides are not equal, it is a contradiction of equation, and this contradiction has arisen just because we have considered 5 minus root 3 as a rational number. It is the contradiction to the assumption. That's why we can say that 5 minus root 3 is the rational number. I have given separate exercise in the different video. In that video, you will find various questions depending on the concepts covered in the lesson real numbers.